Hi, this problem is looking at calculating the torque acting on a CD as it plays for a time of about 1 hour. So to figure out what's going on, we need to talk a little bit about what shape a CD is and look at some typical data for a CD. If it's playing with usual music playback, it'll start moving around 500 revolutions per minute and gradually slow to about 200 revolutions per minute as the reed arm of the CD works its way from the inner grooves out towards the outer grooves. So there are a couple of ways we could go about figuring out the torque and figuring out the acceleration. We could calculate acceleration if we had enough kinematic data to do that, but we could also make use of Newton's second law for rotation, which states that the net torque acting on any object is the change in angular momentum of that object. Well, a CD is essentially a cylinder rotating around its center of mass, which means that the inertia for a CD is going to approximately be 1/2 times the mass of the CD times the radius of a CD squared. So the CD in question has a diameter of 120 millimeters. That means the radius is 60 millimeters or 0.060 meters. A typical CD has a mass of around 16 grams or 0.016 kilograms. So if I take those 1/2 times my mass times my radius squared, a CD has a moment of inertia around its center of about 2.9 times 10 to the negative 5 kilogram meters squared, but since this isn't the end, I'm using it in a later calculation. Let's use 2.88 times 10 to the negative 5 kilogram meters squared for any later calculations. So for an object where we don't necessarily know the instantaneous details of the angular momentum, we can look at the average torque, which would just be my final angular momentum minus my initial angular momentum divided by the time. So in each case, the angular momentum is calculated using the same moment of inertia. So we can take that moment of inertia I and distribute it out, and then we would just need to find our change in angular velocity, omega final minus omega initial. Well, we're told that the initial and final velocities are 500 RPM and 200 RPM respectively, but if we want to calculate everything in proper SI units, with units of newtons and meters and seconds and everything else, we're going to need to convert those units. So for every 1 RPM, there are pi over 30 radians per second. So that means 500 RPM times pi over 30 is going to tell me that the initial velocity was 52.36 radians per second, and the final velocity was 20.94 radians per second. So we have a negative change in velocity of 31.42 radians per second. And 1 hour, 60 minutes is 3,600 seconds. So if I take my inertia times my change in angular velocity divided by my change in time, that gives me a net torque of negative 2.5 times 10 to the negative 7 Newton meters. Now, given that we have the torque, there are a couple of ways we could go about calculating the angular acceleration. We could use the definition of acceleration, our change in angular velocity divided by our change in time. We could use the simple definition of Newton's second law, that the angular acceleration would be the net torque divided by the moment of inertia. We just calculated the torque and the moment of inertia, so let's use that. So if we take negative 2.5 times 10 to the negative 7 Newton meters and divide by 2.88 times 10 to the negative 5 kilogram meters squared, we end up with an acceleration of negative 8.7 times 10 to the negative 3 radians per second squared. Thank you for watching.